You carry a learning machine that runs on almost no power. It's right behind your eyes. Your retina doesn't simply send your brain a picture. It sends the changes, what's moved, what's new, what it didn't expect. The parts of this room that haven't changed, it barely sends a spike on. It reports the surprise and stays quiet on the rest. That isn't a quirk of biology, it's a budget. Intelligence first appeared about 500 million years ago in small animals that had to learn on a few microwatts of power. And the rule was brutal. Learn fast, spend little, or die. So evolution converged on a particular kind of learner, one that pays for what's new and almost nothing for what it already knows. So hold on to that image. A device whose energy bill is its surprise. We built one. I'll show it to you in a few minutes. But first, how differently do we build intelligence today? Ask the question everyone asks. What makes an AI model good? The standard answer is more. More parameters, more data, bigger is better. That's the scoreboard the whole field runs on. On an energy budget, that scoreboard is upside down. This room already knows the next part. The energy in modern AI is not the math. It's moving data to the math engine, dragging weights and activations out of memory for every answer. By the numbers, every architect here knows fetching an operand from memory can cost 100 to 1,000 times the multiplier that uses it. Which is why, when you measure where the energy actually goes, data movement is about 2/3 of it in training and over 80% in inference. The math was never the expensive part. Moving the data to the math is. And at scale, it's staggering. A trillion parameter model moves enormous fractions of itself for a single token. Biology still pays to communicate. Axons and synapses aren't free, but it never makes the central mistake. It doesn't haul a global memory to a separate arithmetic unit for every decision. Memory and compute are the same cells in the same place. So there's a better answer than more. The obvious one, fewer parameters that still do the job. A smaller model is a cheaper model. But there's a better answer still, and it's one that matters. To produce a single answer, you should not have to touch 1,000,000,000,000 parameters at all. You should touch only the handful that actually make that decision, right where they sit. Route the input to the place that decides and wake nothing else. Bringing the decision to the data instead of dragging the data to the decision, that is what we call decision locality. Some of you are already thinking, that's mixture of experts. And you're right, that's the point. The field is already routing instead of waking the whole model for every token. But mixture of experts solves it at the macro level. A handful of experts, each one still a large, dense network. You route to an expert, then light up the entire expert. And because those experts sit on different chips, routing a token means shipping it across the network and back. All-to-all traffic, the fabric pays on every step. Mixture of experts cuts the compute, and that's real. But its locality stops at the expert's edge, and it buys that routing by adding movement back. We take it all the way down. Not a mixture of a few giant experts, but a mixture of micro experts, millions of elemental learners. Ordinary digital logic, not analog, not spikes, each the size of a single number. And nothing here is a learned gate choosing among 1,000,000 experts. Each learner owns a condition, the input's own content selects which ones apply, and each updates its register in place. No state hauled to a shared unit. The model itself becomes the locality. And it has a deeper name, rooted in Shannon. Learning is a compression problem. A good model is a compressed picture of what it has seen. And this is no metaphor. Shannon measured the information in a message by predicting its next symbol. The shortest code for an outcome is exactly its surprise. Predict the next thing well, and you have compressed it. A language model plays the same game with the next token. We play it with the next bit. Inference, then, is a routing problem. Answering means waking only the slice of the model that decides. Learning is compression, inference is routing. And routing to the smallest place that can answer it is decision locality. That's the whole thesis. Everything left in this talk is one question. What's the smallest device that can actually do it? Go all the way down to first principles. The simplest thing you can predict is a single bit. Will the next one be a 1 or 0? And that may not just be the simplest thing, it may be the oldest. The first animal that could learn was answering one binary question over and over. Approach or avoid, delicious or dangerous. The bit we start from may be the bit that life started from. So that is where we started. Picture a probability as a pie, red for the chance the next bit is a 1, blue for a 0, and a thin, unfilled wedge for what it's still unsure about, the wedge of uncertainty. The whole state is a single integer. Low numbers are coarse, a wide wedge. High numbers, fine and hard won. It adds precision only when the evidence earns it. Operationally, that's the whole interface. One integer of state, one input bit, and a few random bits in, one predicted bit out, and a conditional masked XOR right. Compare that to the usual way. Say we have 3 samples, 2 of them are 1s and 1 0. The textbook hands you a 0.66666, 18 digits of confidence from 3 observations. And that precision is a lie. It isn't free. Ours stays coarse and says, honestly, I don't know yet. Converging to the answer, not calculating it, and it's far cheaper. How does it predict? It throws a dart. It lays a handful of random bits against its stored state and reads off the answer. The randomness strips out what we already expected so that what's left is the surprise. And it's cheap. A small LFSR per tile, we measured that these pseudo-random bits give the same accuracy as true random. No entropy bottleneck. Then the data lands in one clock tick. Right? The state holds, nothing moves, nothing spent. Wrong? One slice nudges towards the truth. A single masked XOR, no adder, no multiplier, no carry chain. And when the dart lands in the wedge, the pie earns one more bit. And notice, it predicted and learned in the same step. No separate training run, no external labels, backprop, no gradients. It learns while it runs, one bit at a time for as long as it's on. That's the whole element. Look at when it writes to memory, the expensive part. Only when it's surprised. The clocks and compares run regardless, but the costly act, writing state, is paid in proportion to surprise. That is Shannon made physical. The durable write, the part that changes the model, is paid in proportion to information, and the energy bill is the compressed size of his experience. And it's elemental. The bit is just a 0 or a 1. The NAND gate only inverts or ignores. A transistor only switches or amplifies. Nobody ever asks, what good is one of those? You use them by the millions. The estimator is the next device on that list, the elemental unit of learning. And its entire job is the same 2 moves as the humble NAND. Surprised, it inverts. Expected, it ignores. One thing that is not. This is not neuromorphic. No spikes, no analog membranes, no trained weights. It is a bit serial integer learner with an exact closed form distribution. You can write down what it believes exactly at every step. One estimator tracks one probability. Do they compose? Wire 3 of them together to estimate a conditional probability. Does stream B depend on stream A, and how? And nowhere in that update path is there a matrix multiply. In simulation, 3 composed estimators reach about half the error of 3 carefully hand-tuned exponential filters in both steady and shifting conditions. And here's why that matters. Those filters need a hand-picked smoothing rate. Ours has no knob to turn. There was nothing to tune. And here, the two energies pull apart. Changing state we've tied to surprise, the smaller cost. Moving data is the one that dominates, and the one that explodes the instant you scale. One estimator is the element, a million of them is the system. That million is only possible because of locality. Each computes where its own state already lives. Do it the other way, shuttle every learner's state to a shared math unit, and at a million learners clocked at a gigahertz, that's on the order of a petabyte a second of state traffic before a single byte of real input has moved. No one would build exactly that, but the same scaling creeps back into any shared ALU cluster. Our path sidesteps it. The comparison happens where the state is stored, so the state never has to be hauled to a shared compute unit. You scale by adding learners, not by adding traffic. And here, compression and routing meet. Learning builds a fabric of tiny local models. Inference wakes up only the few that decide. The dense model instinct makes every answer depend on a vast active footprint. Ours collapses that to a few learners that decide. That is decision locality, realized in silicon. Attacking the dominant cost at its source, not making data movement cheaper, but removing the movement that never needed to happen. That is the aim. Tomorrow's AI run towards biology's energy budget. And it quietly dissolves the line your whole stack is built on. Today, AI lives in two worlds, training clusters, then inference fleets. Here, there is no line. Learning and inference are the same operation. So the model keeps learning after it ships, out where the data actually is. A sensor, a phone, a machine on the floor. The always-on places a power-hungry GPU can't follow. And this is not a thought experiment. The element is heavy in foundation. Compare its running estimate to classical Bayesian inference, and at every observation count, it lands between two of the most principled rules in statistics, Jeffreys on one side, Bayes-Laplace on the other. It is sandwiched between them, provably, and it converges at a rate of 1 over t times the natural log of 2, all without ever storing a prior, a likelihood, or a posterior. That is the weight in this foundation. But it is light at runtime. A comparison in an XOR. On an FPGA, a Xilinx Alveo U200, the 8-bit learner synthesizes to 48 lookup tables and 8 registers at 96 megahertz. No multiplier, no adder, and we have first silicon now. A proof of concept chip at TSMC in standard CMOS. In packaging and test, not yet characterized. No exotic physics, no new materials, just the decision brought to the data. And because it's a genuinely different substrate, it leaves open problems for this room. There's no batch dimension to schedule around. Energy is metered per bit, not per layer. And the honest hard part, selecting learners is content addressed, but physically routing inputs across a million learner fabric and scheduling it is open territory, the kind this workshop exists for. This talk was one of 4 ISCA talks, and it was the architecture. And here is why I'll risk the comparison. A NAND gate is universal. Every logic circuit can be built from it alone. We proved the learning analog. Compose a small number of these estimators, they discover all 16 two-input Boolean functions, including XOR, the one that famously broke the perceptron, with no backpropagation. Compose further, and they capture larger circuits, A equals B, or not C and D. Learned as probabilities, not certainties. So the pieces compose. The hard part is the architecture question, how to discover, place, and schedule the pieces a problem needs. And that is what the companion talks take on. The proofs in MLArchsys, the scaling in CogArch this afternoon, a pool of learners, and an interrogative architecture reading handwriting digits past 98%. No backpropagation. And building block discovery in Mizark, which handed nothing finds a 1,000 element symmetry group on its own. For 50 years, the industry has chosen to calculate. We choose to recognize the way the eye does under a brutal energy budget. We think this is the transistor of AI.